Chapter 2, Computer Graphics. CAD engineer should know the software development process in computer graphics. This chapter discusses in detail basic output primitive in computer graphics. The knowledge of 2D output primitives helps in developing software. The line clipping algorithm and solid modeling are also introduced in this chapter. Learning objectives. Number 1. Learners will be able to write a computer program for basic graphical primitives. Number 2. Learners will be able to perform a transformation on any graphical entity. Number 3. Learners will be able to understand the importance of windowing and solid modeling. Para 2.1 Introduction. CAD hardware cannot do anything on its own unless a sequence of instructions to perform to get the desired output are specified. Such a sequence of instructions written in language that can be understood by a computer is called a computer program. The term CAD software refers to a state of computer programs, procedures, and associated documents that describes the program and how they are used from the point of view of the design of a mechanical part. To be precise, CAD software means the collection of programs whose objective is to enhance the capabilities of CAD hardware. CAD software is the state of one or more programs designed to carry out operations for a specified design applications. For example, drafting package AutoCAD produces drawing of a mechanical part as the major output, and the finite element method software produces an analysis of design as a major output along with some other statistical reports. Similarly, a program written by CAD engineer for the design of the gear is also CAD software. Para 2.1.1 Software Operations. The various CAD software is developed that is capable of handling CAD processes such as drafting, analysis, optimization, etc., and gives the result when the user provides the necessary inputs. For example, if the user gives the center and radius of a circle, AutoCAD software produces a circle on the screen as output. Users need not know how the circle gets drawn, that is, how the software for the drawing circle is developed. This aspect is called software operation. The user is trained only to operate already developed software. Para 2.1.2 Software Development. The development of the software, that is writing computer program, is an important area or field where CAD engineers should be trained. Software development should be handled only by an experienced and knowledgeable person or engineer. For software development, the knowledge of at least one computer programming language is expected. In this chapter, the main focus will be on the concept of software development in computer graphics. Para 2.2 Output Primitives. CAD engineer uses a computer for two tasks. Number 1, to write a computer program for the design of a mechanical part. Number 2, to edit or draw a drawing of the mechanical part designed in task 1. Out of the above two tasks, the first task can be accomplished if the knowledge of computer language is known. By using languages like Fortran, C, C++, it is possible to develop a computer program or software for the design of the mechanical part. Once the design parameters like the diameter of the shaft, length of the shaft, etc. in case of shaft design are known, it should be possible for CAD engineer to embed the graphics program in the program of design of mechanical part, as a drawing of the design part is the essential and necessary output. Editing the graphics is a difficult task because in such cases it should be known how to develop computer graphics program. This is because the procedure or algorithm related to the graphical entity is not known. In order to understand the development or representation of graphics on computers, the concept of output primitives is used. The output primitives are the building blocks of the drawing. It is known to us from the concept of mathematics that graphical entities like line, circle, etc. are made of points. Thus, a point can be considered as a basic building block of the drawing. It is important to note the representation of a point on the computer. The point is represented as a dot on a paper. This can be considered analogously the representation of the phosphor dot. The phosphor dot representation on the screen is the point. It is difficult to use a point as the only building block because drawing consists of large number of points, and hence representing all such points on computer screen by user is a difficult task. For the convenience of the user, the output primitives are considered under two categories. Number 1, linear element, that is line. Number 2, curved element, that is circle. It is now necessary to know the algorithm for the development of the line and circle. The basic input for the generation of the line is the end points of the line, while in case of the circle, it is center and radius. The procedure in a line generation is to find pixels on points lying on the path of the line. The illumination of the pixels on the path of the line is the representation of the line on the computer. Refer figure 2.1. Similarly, in the case of a circle, points or pixels over the path of the circle, that is, on the periphery of the circle, are found out using circle generation algorithm. The illumination of pixel over the path of the circle is the representation of a circle on the computer. Refer figure 2.2. Para 2.3. Line generation algorithm. There are two types of algorithm used for line generation. Number 1, digital differential analyzer DDA. Number 2, Breschnem's algorithm. In both these algorithms, certain common features are incorporated. If the two endpoints of the line are known, then slope of the line can be found out. The slope of the line m is given as m equals to delta y by delta x. Therefore, delta y is equals to m delta x. In equation, there are three terms, delta y, m and delta x. If any two terms are known, then third can be found out. It is possible to set changes in x coordinate or y coordinate, that is delta x or delta y, to 1 and then find the change in other coordinate and hence coordinate of the succeeding point. If the slope of the line is less than 1, then span or change in x coordinate is more than span or change in y coordinate. Refer figure 2.3. In such cases, it is desirable to keep delta x to be unity so that more number of pixels on the path of the line can be found out. Similarly, for a line having slope greater than 1, it is desirable to set delta y to be unity so that more number of points or pixels on the path of the line can be found out. Refer figure 2.4. DDA algorithm. DDA algorithm is not discussed in the audiobook as it is not used. Para 2.3.2 Breschnem algorithm. Two important points must be noted in the case of Breschnem algorithm. Number 1, the line is always drawn from left to right, irrespective of input from the user. Out of the two endpoints given by the user, Breschnem algorithm decides the point which is lying to the left as the starting point. Number 2, the equation of the line y equal to mx plus c is used to generate a line where c is the y-intercept. Case 1. Slope of the line is positive and less than 1. As the slope of the line is less than 1, increment in x coordinate is set to unity, that is delta x equals to 1. Let xi yi be any point on the line. The x coordinate of the next point will be xi plus 1, while y coordinate of the next point, that is yi or yi plus 1, is decided by defining two parameters d1 and d2 as d1 equals to y minus yi, d2 equals to yi plus 1 minus y, where y is equals to m into xi plus 1 plus c. Refer figure 2.5. Substituting the value of y in the expression of d1 and d2, we have d1 equals to m into xi plus 1 plus c minus yi, d2 equals to yi plus 1 minus m into xi plus 1 minus c. With these equations, the parameter pi equals to delta x d1 minus d2 is defined. It can be written as pi equals to 2 delta y xi minus 2 delta x yi plus b, where b is equals to 2 delta y plus delta x into 2c minus 1. The value of b remains constant for the complete line. The value of pi is evaluated to decide the pixel. If pi is less than 0, then select the pixel at position yi, as y is nearer to yi compared to yi plus 1. If pi is greater than or equal to 0, then select the pixel at position yi plus 1, as y is near to yi plus 1 compared to yi. The procedure is continued till we reach the other endpoint of the line. In this procedure, there is no rounding of operation, only the value of pi is to be evaluated. The expression of pi consists of simple arithmetic expression which can be evaluated at a faster rate on the computer. Case 2. Slope of the line m is greater than 1 and positive. In this case, change in the y coordinate, that is delta y, is set to unity. The procedure is the same as explained in case 1, except delta y and delta x are interchanged in the expression of pi. Case 3, slope of the line is negative. In this case, the absolute value of m is considered and the procedure as laid down in case 1 and case 2 is followed except one coordinate increases while other decreases. A computer program for line generation. In order to generate the point on the line using Breschnum line algorithm, the value of the pi parameter is evaluated, which is defined for any point xi yi as pi equals to 2 delta y xi minus 2 delta x yi plus b, where b is equals to 2 delta y plus delta x 2c minus 1. In order to decide the next pixel or the point after starting point xi yi, the value of pi is evaluated. It is thus necessary to know the value of pi parameter for the starting point in order to find the next point using Breschnum algorithm. The value of pi parameter for the starting point is evaluated as follows. Let x1 y1 be the starting point. From equation of the line y equal to mx plus c, we know y1 is equal to mx1 plus c. C is equals to y1 minus mx1. That is c equals to y1 minus delta y by delta x into x1. Substituting the value of c in b, we have b is equals to 2 delta x y1 minus 2 delta y x1 minus delta x plus 2 delta y. Substituting the value of b in expression of pi, which is represented as p initial, as this is the pi for the initial point, we have p initial equal to 2 delta y minus delta x. In computer program, p initial is represented by variable p. Delta y is represented as dy and delta x is represented by dx. To evaluate every time the pi parameter for all succeeding points, it is desirable if the relation between the pi parameter of two succeeding points is established. This means if the value of the pi parameter is known, then the value of pi plus 1, that is the pi parameter for the next point, can be found out without going for the complete expression of pi as obtained in Breschnum algorithm. It can be shown that if pi is less than 0, pi plus 1 is equals to pi plus 2 delta y. If pi is greater than or equal to 0, pi plus 1 is equals to pi plus 2 delta y minus delta x. The computer program in C language is shown in Kindle version of book. Para 2.4, Circle Generation Algorithm. In order to generate this circle, the basic input is the center and the radius of the circle. Using the circle generating algorithm, the pixels lying on the path of the circle are found out. The illumination of such pixel is the representation of a circle. There are two types of the circle generating algorithm. Number 1, using the conventional equation of circle in Cartesian or polar coordinate. Number 2, Breschnum algorithm. The circle generation using conventional equation of circle is not discussed in audiobook as it is not recommended. Para 2.4.3, Breschnum algorithm. Breschnum algorithm uses the symmetry of the circle extensively. It can be proved that if 1/8 part of the circle is generated, the rest 7/8 part of the circle can be generated using symmetry. This is clear from figure 2.8. In Breschnum algorithm, the procedure is defined for only 1/8 part of the circle and hence the development of software is very easy. The circle also gets drawn at a faster rate. In Breschnum algorithm, the procedure is started from the topmost point, that is 0r, if the equation of the circle is x square plus y square equals to r square. The x coordinate of the point increases while the y coordinate of the point decreases. At one point, value of x coordinate and y coordinate will be the same. At that point, the procedure is stopped because 1/8 part of the circle gets created. Refer figure 2.9. The equation of the circle used is x square plus y square equals to r square. Let xi, yi be any point on the circle. The x coordinate of the next point will be xi plus 1. The y coordinate of the next point, that is yi or yi minus 1, is decided by defining the parameter d1 and d2. Refer figure 2.10. d1 can be defined as d1 equals to y square minus y square. d2 is equals to y square minus y minus 1 whole square, where y square is equal to r square minus xi plus 1 whole square. With these two equations, the parameter pi is defined as pi equals to 2 into xi plus 1 whole square plus yi square plus y minus 1 whole square minus 2r square. If pi is less than 0, then select the pixel at position yi, as yi is near to y than yi minus 1. If pi is greater than or equal to 0, then select the pixel at position y minus 1, as y minus 1 is nearer to y than yi. The procedure is continued until we reach the 1/8 part of the circle. In this procedure, the pi expression is to be evaluated, which consists of a simple arithmetic expressions. This can be done at a faster rate. The procedure being simple, software development is easy. There is no rounding of operation. Hence, this algorithm is used in CAD application. The procedure explained above is for the circle with 0, 0 as the center. This can be extended for the circle with center XCYC. For the circle with XCYC as the center, to every x coordinate generated by the above procedure, add XC, and to every y coordinate generated, add YC. Computer program for circle generation. The points over the path of the circle are generated if the value of pi parameter is calculated or evaluated. We know pi is equals to 2 into xi plus 1 whole square plus y square plus y minus 1 whole square minus 2r square. This parameter pi is for the point xi yi. By evaluating this value of pi, it is possible to know the next point after xi yi. It is essential to know the value of pi parameter for the starting point in order to proceed with Breschnem circle algorithm. The initial or starting point is 0r. The pi parameter for the initial point, that is p initial, can be found out by substituting xi yi equals to 0r, and we get p initial is equal to 3 minus 2r. P initial is represented as variable p in the computer program. To evaluate every pi parameter for all succeeding points, it is desirable if the relation between the pi parameter of two succeeding points is established. This means if the value of pi parameter is known, then the value of pi plus 1, that is the pi parameter for the next point, can be found out without going for the complete expression of pi as obtained in Breschnem algorithm. It can be proved that if pi is less than 0, then pi plus 1 is equal to pi plus 4xi plus 6. Similarly, if pi is greater than or equal to 0, then it can be proved that pi plus 1 is equals to pi plus 4 into xi minus yi plus 10. The computer program in C is shown in Kindle version of book. Para 2.5 Ellipse Generation. The Breschnem algorithm for a circle can be extended to generate the ellipse. The equation of the ellipse is x square upon a square plus y square upon b square equals to 1. A and B are semi-axes along x and y direction. The procedure of finding the pi parameter is the same as that of a Breschnem circle algorithm. In the case of the ellipse, 1/4 part is generated and rest 3/4 part is found out by symmetry. Refer figure 2.11. Para 2.6 Arc Generation. For the arc generation, 3 inputs are necessary. In addition to 2 endpoints, one more input for the arc is necessary. That is either center of the arc or radius of arc or angle included in the arc, etc. The arc can be generated using the equation of a circle in polar coordinate form as x equal to xc plus r cos theta, y is equal to yc plus r sin theta, where theta is the angle made by a radical vector with positive x-axis and xcyc is the center of the arc. Theta is varied from theta 1 to theta 1 plus theta 2 in the steps of unity to generate the points on the arc. Refer figure 2.12. This procedure involves the use of trigonometric functions and hence not recommended. The procedure can be used if the span of the arc is less. If the span of the arc is very large, as shown in figure 2.13, then Breschnem algorithm for the circle can be used to draw such an arc, wherein the generated points are tested for the limit specified by the points A and B. Para 2.7 Plane curve. Any curve on the computer can be generated if its equation, namely y equal to fx, is known. Refer figure 2.14. The x-coordinate is varied within the minimum and maximum value in the steps of unity and the corresponding y value is found out. For the generation of the curve, when the slope is greater than 1, the equation is written as x equal to f inverse y. That is, x is expressed in terms of y and y is varied within the range and correspondingly x is found out. The procedure is adopted for generating any plane curve such as conic, logarithmic curve, normal distribution curve, etc. Para 2.8 Transformation. The modification or manipulation of edited drawing can be carried out using transformation. There are 4 transformations which are used in computer graphics, namely number 1 translation, that is move, number 2 scaling, number 3 rotation, number 4 reflection. Out of these 4 transformations, the first 3 are fundamental transformation. The reflection transformation is studied using the fundamental transformation. Para 2.8.1 Translation. Using translation, it is possible to translate or move a graphical entity from one location on the screen to the other. Consider a line AB and its translated image A1B1 as shown in the figure 2.15. Tx represents the distance in the x direction while Ty represents the distance in the y direction. It is clear from figure 2.15 that the point A is shifted to A1 and to the x coordinate of A, Tx is added, and to the y coordinate of A, Ty is added. X dash y dash, that is the coordinate of A1, can be obtained using the following relation: x dash equal to x plus Tx, y dash equal to y plus Ty, where Tx, Ty is called translation vector. The values of Tx and Ty are user input. Using the equation, it is possible to find coordinate of any point over the line A1B1 and hence the line A1B1 can be drawn. In practice, the translated image of endpoints are found out using the relation, and the Breschnum line algorithm is run between the two translated points to obtain translated image of the line. Para 2.8.2 Scaling. Using scaling, it is possible to enlarge or reduce the graphical entity. The general equation of scaling is x dash equal to x into sx, y dash is equal to y into sy, where x dash y dash is the scaled image of the point xy. Sx and sy represent the scaling factor in x and y direction. If sx, sy is greater than 1, then complete graphical entity is enlarged. If sx and sy is less than 1, then complete graphical entity is reduced, that is becomes smaller in size. If sx and sy is equals to 1, then uniform scaling is obtained in which there is no change in the shape of the object. If sx is not equal to sy, then non-uniform scaling is obtained in which the shape of the object changes. It is clear from the equation that while scaling the object, translation also takes place. Because of the translation, the translated object may go out of the screen limit. The part of the object which goes out of the screen limit may appear from the other side of the screen. This is called wraparound effect. Wraparound effect is to be avoided because it disturbs the original drawing. The wraparound effect is minimized if the scaling with respect to fixed point xf yf is executed. The equation for the scaling with respect to the fixed point can be proved as x dash equal to x into sx plus 1 minus sx into xf, y dash equal to y into sy plus 1 minus sy into yf. This is discussed in detail in section 2.8.5. Para 2.8.3 Rotation. In this transformation routine, the point or graphical entity is rotated about the point. In order to execute the rotation, it is necessary to know 3 inputs. Number 1, the angle of rotation. Number 2, the point about which rotation is carried out. Number 3, direction of rotation. Consider a point xy rotated about origin as shown in figure 2.17. Figure 2.17 illustrates the rotation process of a point xy. It can be written as x equal to r cos phi and y equal to r sin phi. Similarly, x dash equals to r cos theta plus phi and y dash equal to r sin theta plus phi, where theta is the angle of rotation, r is the radial vector, phi is the angle made by the radial vector with the positive x-axis. The general representation of equation of rotation can be written as x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta. It may be noted that the above expression is for the anticlockwise rotation of a point. If the direction of rotation is clockwise, then theta is replaced by minus theta in the equation. If rotation is carried out about any point x or y r, then equation of rotation can be proved as x dash equal to xr plus x minus xr cos theta minus yr sin theta, y dash equal to yr plus x minus xr sin theta plus y minus yr cos theta. This is discussed in detail in section 2.8.5. Para 2.8.4, concatenation, matrix representation or homogeneous coordinate. If on a graphical entity more transformations are performed one after the another, then final transferred image of the graphical entity can be found out using the algebraic equation as explained below. If a point is first translated, then it is scaled, and finally it is rotated, then its final transferred image can be found out by writing algebraic equation for translation, then scaling, and finally for rotation. And the final transferred image x3 dash y3 dash thus can be obtained. If the number of transformations are more, then use of algebraic equations will become tedious, and hence use of equation in matrix form is simpler. To write the matrix equation, it is necessary to express the point xy in matrix form as xy1. This is called homogeneous coordinate representation of the point. Translation. To write the algebraic equation of translation in matrix form, the transformation matrix for translation can be written as 3 by 3 matrix as 1 0 0 0 1 0 tx ty1. The matrix equation for the translation of the point xy by the translation vector tx ty can be written as xy1 into 1 0 0 0 1 0 tx ty1, that is x plus tx y plus ty 1. Scaling. The transformation matrix for the scaling can be written as sx00 0sy0 001. The scaled image of the point xy by the scaling factor sx and xy can be obtained using matrix equation as xy1 into sx00 0sy0 001, that is x into sx y into sy1. Similarly, the transformation matrix for the scaling with respect to the fixed point can be written as sx00 0 sy0 1 minus sx sf 1 minus sy yf 1. Rotation. The transformation matrix for the rotation about the origin can be written as cos theta sin theta 0 minus sin theta cos theta 0 0 1. The transferred image of the point xy after rotation about the origin in the clockwise direction can be obtained using the matrix equation as follows: xy1 into cos theta sin theta 0 minus sin theta cos theta 0 0 1. Similarly, the transformation matrix for the rotation about any point xr yr can be written as cos theta sin theta 0 minus sin theta cos theta 0 xr 1 minus cos theta plus yr sin theta yr 1 minus cos theta minus xr sin theta 1. Using transformation matrices, it is possible to write a matrix equation for the composite transformation. As explained above, if the multiple transformations like translation, then scaling, and finally rotation is executed on the point xy, then final image of the point xy can be obtained by using the matrix equation as follows. Let A represents the transformation matrix for the translation. Let B represent the transformation matrix for the scaling. Let C represent the transformation matrix for the rotation. The matrix equation can be written in one step as x3 dash y3 dash 1 is equal to xy1 into A into B into C. The final transferred image of the point xy, that is x3 dash y3 dash, can be obtained by using any number of transformation and the type of the equation. The process of finding the transferred image of the point by multiplying the matrices in order is called concatenation. Para 2.8.5 Application of concatenation. Using the concatenation process, it is possible to prove the relation for scaling with respect to a fixed point xf yf and rotation about any point xr yr. Similarly, the concatenation process is used for studying the transformation reflection. Scaling with respect to fixed point. The relation for scaling with respect to fixed point is given as x dash equal to x into sx plus 1 minus sx into xf, y dash equal to y into sy plus 1 minus sy into yf. This relation can be proved using concatenation process as: consider a triangle ABC as shown in figure 2.18. The scaling of the triangle ABC with respect to xf yf can be obtained using three transformations. Point xf5 is first translated so that it coincides with origin. Let A represent the transformation matrix for translation. A is equals to 1 0 0 0 1 0 minus x minus 5 1. The triangle is then scaled about the origin. Let B represent the transformation matrix for scaling. B is Sx00, 0sy0, 001. Finally, the point is shifted, that is point which coincides with origin, back to xf5 position so that the original point is stored. Let C represent the transformation matrix for translation 1 0 0 0 1 0 xf5 1. The final transformation matrix for the scaling with respect to a fixed point xf5 can be obtained by concatenating A, B, C. The R, that is the final transformation matrix, can be written as Sx00, 0sy0, 1 minus Sx into xf, 1 minus sy into yf, 1. The transferred image of the point xy after scaling with respect to the fixed point, that is x dash y dash, can be obtained as x dash equal to x into sx plus 1 minus sx into xf, y dash equal to y into sy plus 1 minus sy into yf. Rotation about any point xr yr. The relation for rotation about any point xr yr is given as x dash equal to xr plus x minus xr cos theta minus yi minus yr sin theta, y dash equal to yr plus x minus xr sin theta minus y minus yr cos theta. This relation can be proved using concatenation process as: consider a triangle ABC as shown in figure 2.19. The rotation of the triangle ABC about any point xr yr can be obtained using three transformations. Number 1. Point xr yr is first translated so that it coincides with origin. Let A represent the transformation matrix for translation. A is given as 1 0 0 0 1 0 minus xr minus yr 1. Number 2. The triangle is then rotated about the origin in the clockwise direction. Let B represent the transformation matrix for rotation and is given as cos theta sin theta 0 minus sin theta cos theta 0, 0 0 1. Number 3. Finally, the point is shifted, that is a point which coincides with origin, back to xr yr position so that the original point is restored. Let C represent the transformation matrix for translation. C is given as 1 0 0 0 1 0 xr yr 1. The final transformation matrix for rotation about any point xr yr can be obtained by concatenating A, B, C. So, the final transformation matrix R will be equal to A into B into C. R can be expressed as cos theta sin theta 0 minus sin theta cos theta 0 minus xr 1 minus cos theta plus yr sin theta, yr 1 minus cos theta minus xr sin theta 1. The transferred image of the point xy after rotation about any point xr yr, that is x dash y dash, can be obtained as x dash equal to xr plus x minus xr cos theta minus yi minus yr sin theta, y dash equal to yr plus x minus xr sin theta minus y minus yr cos theta. Reflection. In this transformation, mirror image of the graphical entity is obtained. This is possible if the axis of reflection is defined. Consider the coordinate axis as axis of reflection. Refer figure 2.20. If the reflection of the point xy is obtained about x-axis, then x-coordinate of the point remains the same while y-coordinate flips. The transformation matrix for the reflection about x-axis can be written as 1 0 0 0 minus 1 0 0 0 1. Similarly, if the reflection is obtained about y-axis, then y-coordinate remains the same while x-coordinate flips. The transformation matrix for the reflection about y-axis can be written as minus 1 0 0 0 1 0 0 0 1. If the axis of reflection is a line passing through the origin and perpendicular to x and y, then both the coordinate, that is x and y, flips. The transformation matrix for this axis of reflection is given as minus 1 0 0 0 minus 1 0 0 0 1. It is clear from the above discussion that for any reflection axis, a unique transformation matrix is defined. It is therefore necessary to know the generalized procedure for obtaining the transformation matrix. Reflection about line y equal to mx plus c. The transformation matrix for the reflection about axis y equal to mx plus c can be obtained using the concatenation process. The procedure of obtaining the transformation matrix is as indicated below. Consider a point P as shown in figure 2.21. The transferred image of the point P after reflection about the line y equal to mx plus c is P dash. The point P dash can be obtained by concatenating 5 transformations. Number 1. The line y equal to mx plus c is first translated by c unit in negative y direction so that it passes through the origin. Let A represent the transformation matrix for this translation. A can be written as 1 0 0 0 1 0 0 minus C1. The point P takes the position as P1. Number 2. The line is then rotated by an angle theta in the clockwise direction so that it coincides with x-axis. Let B represents the transformation matrix for the rotation. B can be written as cos minus theta sin minus theta 0 minus sin minus theta cos minus theta 0 0 0 1. The point P1 takes the position as P2. Number 3. The reflection of a point P2 about the line which coincides with x-axis can be found out. Let C represents the transformation matrix for this reflection. C can be written as 1 0 0 0 minus 1 0 0 0 1. The point P2 takes the position as P3. Number 4. The line is then rotated by an angle theta in an anticlockwise direction. Let D represent a transformation matrix for the rotation. D can be written as cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. The point P3 takes the position as P4. Number 5. Finally, the line is translated by C unit in a positive y direction so that original position of the line is restored. Let E represent the transformation matrix for this translation. E can be written as 1 0 0 0 1 0 0 C1. The point P4 takes the position as P dash. P dash is the reflected image of the point P about line y equal to mx plus c. The final transformation matrix of reflection about line y equal to mx plus c can be obtained by concatenating A, B, C, D, E. Thus, R can be represented as A into B into C into D into E. If the axis of reflection is passing through the origin, that is y equal to mx, then concatenation of only 3 transformation matrices is required. Para 2.9 Windowing and Clipping. Whenever the part of the drawing is to be modified, the concept of window is used. Window is defined as a rectangle created by user over the computer screen. By creating a window, part of the drawing is selected. The drawing entity selected by window is then shown in the viewport. The size of the viewport can be varied. It can extend up to the screen limit. In figure 2.22, part of the drawing selected by the window is shown on the viewport PQRS. It is thus necessary to have viewport when the window is created. By creating a window, some part of the drawing is selected, that is clipped. In the figure, part D1E of the line DE is clipped. Similarly, part A1E of the line AE is clipped, and so on. Windowing is always associated with clipping. There are 2 types of clipping techniques: point clipping, line clipping. Point clipping is used for selecting the part of the non-linear element of the drawing, while the line clipping is used for selecting the part of the line. Line clipping technique can be studied using 2 algorithms, namely, number 1, Cohen-Sutherland algorithm, number 2, midpoint subdivision algorithm. Point clipping technique. Any point Pxy is selected for the window based on its position with respect to window boundary. Consider the window and its associated vertices as shown in figure 2.23. Point xy is inside the window if it satisfies the following inequalities: xw mean less than or equal to x less than or equal to xw max. Yw mean is less than or equal to y less than or equal to yw max. If any one of the inequalities is not satisfied, then the point is outside the window and it is not clipped. It is important to note that the point on the window boundary is always inside the window. Para 2.10 Line clipping technique. Para 2.10.1 Cohen-Sutherland algorithm. Using the Cohen-Sutherland algorithm, it is possible to clip the line for the window. The lines are divided into 3 classes by considering their orientation. Number 1, the line is completely inside the window. Number 2, line is completely outside the window. Number 3, the line is cutting the window boundary. The line which is lying completely inside the window is clipped. The line which is completely outside the window is not clipped, while for the line which is cutting the window boundary, part of the line lying inside the window is clipped. The orientation of the line is decided by dividing the complete screen into 9 regions or domains. Every region is coded by a 4-bit number. The central region is the window and it is coded as 0000. The region coding is done using the following procedure. Considering the rightmost bit as the first and leftmost bit as the fourth, the regions which are lying to the left of the window will have 1 in its first bit position. The region which is lying to the right of the window will have 1 in its second bit position. The region which is lying above the window will have 1 in its third bit position. The region which is lying below the window will have 1 in its fourth bit position. The region codes for all the regions are as indicated in figure 2.241. Endpoints of the line are assigned region codes based on their position with respect to the window. The line is completely inside the window. If the region codes of both the endpoints of the line are 0000, then the line is completely inside the window and it is selected. The line is completely outside the window. If one appears at the same bit position in the region code of both the endpoints of the line, then the line is completely outside the window. The line PQ is completely inside the window because the region codes of P and Q is 0000. The line MN is completely outside the window because one appears at the first bit position in the region codes of M and N. Line cutting the window boundary. For the line cutting the window boundary, part of the line inside the window is selected. In such a case, the endpoints of the line are observed for its position with respect to window boundary. Based on the position of any one endpoint of the line, the point of intersection of the line with window boundary is found out. The other endpoint of the line is then observed. Based on its position with respect to the window, part of the line is then clipped. Refer figure 2.25. For line PQ, point P lies below the window and hence the point of intersection of the line PQ with the bottom boundary of the window, that is P1, is found out. The part PP1 of the line is rejected because it lies outside the window. The other endpoint of the line, that is point Q, lies above the window. Hence the point of intersection of the line PQ with the upper boundary of the window, that is Q1, is found out. The part QQ1 of the line is rejected because it lies outside the window. The part P1Q1 of the line PQ is clipped because it lies inside the window. For line MN, M lies to the left of the window. The point of intersection of the line MN with respect to the left boundary of the window, that is point M1, is found out. The part MM1 is not clipped as point M1 also lies outside the window. The other endpoint of the line, that is N, lies outside the window and so the point M1, hence the complete line MN, is not clipped. Using the Cohen-Sutherland algorithm, the orientation of any line can be decided. This is very simple technique used for clipping, hence it is used in CAD application. Para 2.10.2 Midpoint Subdivision Algorithm. In the Cohen-Sutherland algorithm, for analysis of line cutting the window boundary, the point of intersection with window boundary is to be found out. This can be avoided using a midpoint subdivision algorithm. In this algorithm, midpoint of the line is found out. The line is divided into two parts. The part of the line which is completely inside the window or outside the window is completely selected or completely rejected. For the part of the line cutting the window boundary, its midpoint is found out and it is again analyzed. This procedure is repeated until the midpoint falls on the window boundary. Refer figure 2.26. The midpoint of the line PQ, that is P1, is found out. The line PQ is divided into two parts, part PP1 and part P1Q. The part P1Q is completely inside the window and hence it is selected. The part PP1 is cutting the window boundary, hence its midpoint P2 is found out. Part PP1 is divided into two parts, namely PP2 and P2P1. Part PP2 is completely outside the window, hence it is rejected. Part P2P1 is cutting the window boundary and hence its midpoint P3 is found out. This procedure is repeated until the midpoint falls on the window boundary. Para 2.11 Three-dimensional modeling. The solid modeling CAD software helps the designer to see the designed object as if it were the real manufactured product. It can be seen in various directions and in various views. This helps the designer to be sure that the object looks exactly as they wanted it to be. It also gives additional vision to the designer as to what more changes can be done in the object. There are three main types of 3D models: wireframe model, surface model, solid model. Para 2.11.1 Wireframe model. A wireframe model of an object is the simplest geometric model that can be used to represent the object mathematically on the computer. It is sometimes referred to as a stick figure or an edge representation of the object. It can be imagined that a wire is bent to follow the edges of the object to generate the model, hence it is called a wireframe model. A wireframe model consists of points, lines, areas, circles, conics, curves, etc. Wireframe modeling is considered as a natural extension of traditional method of charting. Wireframe models form the basis for the generation of surface model. Wireframe models are also called as edge vertex models. Wireframe models are created by specifying the points, lines and curves in space to create the model. The interactive terminal screen is usually divided into sections showing the various views of the model. Point, lines and curves created in one view are generally automatically projected into the other views approximately. Good system constructs the line, curves, etc. based on the given specified points by menus of specific commands which can be chosen from a menu displayed on screen. Refer figure 2.27. Advantages. Number 1, simple to construct because of the simplicity of geometric concepts. Number 2, requires less computer time and memory. Number 3, does not require extensive training for user. Number 4, form the basis for surface model and solid model. Number 5, easy to clip and manipulate through the use of geometric and coordinate transformation. Number 6, it can be used in manual finite element modeling and tolerance analysis. Disadvantages. Number 1, there are ambiguous representation of real objects and hence rely heavily on users' interpretation. Number 2, these lacks in visual coherence and information to determine the object profile. For example, a hole is displayed as two parallel circles separated by the length of the hole. Some systems join the circles by the lines, which may introduce problems later during cleanup. Number 3, creation of wireframe model is lengthy in terms of the amounts of defining data and command sequence. Number 4, both topological and geometrical data are needed to construct wireframe models. Number 5, wireframe models cannot be used for cross-sectioning, interference, etc. Number 6, models of complex design having many edges become very confusing to understand and interpret. Para 2.11.2 Surface modeling. The boundary of a solid object consists of surfaces that are bounded by the straight lines and curves. Surface models are models that provide a precise definition and display of surface of the object, including complex surface such as aerodynamic models and turbine blades. A surface model provides the description of an object in terms of lines, curves, and also shaded surfaces. CAD system provide extensive surface menus from which the surface modeling can be easily done. These includes plane surfaces, tabulated cylinders, ruled surfaces, surfaces of revolution and sweep, fillet and sculptured surfaces such as Bezier, B-spline patches, etc. Refer figure 2.28. Advantages. Number 1, complex sculptural surface such as turbine blades, airplane bodies, automobile bodies, etc. can easily be modeled and displayed in surface modeling, giving in the neatly physical appearance of the objects along with visual coherence. Number 2, the confusion created by various lines and curves in wireframe modeling is completely eliminated as surface models provide precise definition and display of surfaces. Limitations. Number 1, the surface model has no knowledge of volume, so it cannot easily be used to calculate mass properties to create sections. Number 2, surface models like wireframe models are incapable of handling the spatial addressability, that is, they are incapable of verifying whether the two objects occupy the same space or not. Number 3, surface models are slow to render and computationally intensive. Number 4, surface modelers store only the geometrical information of the object like wireframe modeler. Para 2.11.3 Solid modeling. A solid model is a complete representation of an object with topological and geometric data, facilitating mass property calculations and permitting functional automation, integration and animation. Number 1, solid models contain both geometric data and topological information of the objects. Geometry is the actual dimensions that define the entities of the object. Topology is the connectivity and associativity of the object entities. Wireframe models and surface models do not contain topological data and hence considered incomplete and ambiguous. Number 2. Solid models can be quickly created without defining individual locations as in wireframe models. In many cases, solid models are easier to build than wireframes or surface model. Number 3. Intersection of two solid surfaces can easily be created in solid modeling, which is not possible in wireframe modeling unless the point of intersection of the curves representing the surface are separately computed, which is cumbersome and time-consuming process, even then leading to ambiguity and confusion. Number 4. Addition or subtraction of entities is easier in solid modeling, whereas it is complicated and confusing with wireframe models. For example, a block with 6 cylindrical holes can be created by creating a block first, and then 6 cylindrical units can be easily subtracted in solid modeling. Creation of a solid model. Creating a solid model usually begins with 2D sketch. Sketch entities are used to create features. The features are the basic blocks of the model. Features are then individual building blocks that when combined make up the part. Some of the common features are extrude, revolve, loft and sweep. Extrude. Extrude are used to create a feature by protruding a section in the normal direction. As with the base, all extrude begins with the section sketch. Revolve. The revolve tool is used to add material by revolving one or more profile around a center line. It is possible to create revolve bases, revolve cuts or revolve surfaces. The revolving feature can be solid, a thin feature or a surface. Sweep. A sweep is used to create a base, boss, cut or surface by moving a profile, that is section, along a path and controlling the shape with the guide curves. It can be simple and complex. Loft. A loft is used to create a feature by making transition between profiles. It can be base, boss cut or surface. It is possible to create a loft using 2 or more profiles. Questions. Number 1. Explain Bresham circle algorithm. Write a computer program which generates a circle where the radius and center of the circle are the user input using Bresham algorithm. Number 2. Explain the concept of basic two-dimensional transformation using matrix method. Number 3. Why Bresham's line drawing algorithm is preferred to DDA algorithm. Number 4. Explain the Cohen-Sutherland algorithm for clipping lines. Number 5. Discuss and differentiate windows and viewport. Number 6. What is interactive computer graphics? Give at least 2 applications of it. Number 7. Write an algorithm to draw an arc with the coordinate of the center, radius, start angle and the end angle of the arc given. Number 8. How to use midpoint subdivision technique for line clipping. Explain with example. Number 9. Explain and write Bresham line algorithm to draw the line between any 2 points and slope less than unity. Number 10. What are the primitives used in solid modeling to create the solid? Tutorial. Write a computer program based on user input. Number 1. To generate line using Bresham algorithm having negative slope. Number 2. To generate ellipse. Number 3. To clip the line cutting the window boundary using Cohen-Sutherland algorithm. Tutorial number 2. As self-study, refer the website to know about the curves like B-spline curve, Bezier curve used in computer graphics. Tutorial number 3. A line from 2 points A 1030 and B 8070 is to be scaled by factor 1.5 in the x direction and 2 in y direction and to be translated by vector 3040. Determine the transformation matrix and coordinates of the transferred line. Tutorial number 4. A triangle having vertices 3, 3, 8, 5, 5, 8 is first translated by 3 units in x direction, then it is scaled by 2 units about a fixed point 5,6 and finally it is rotated about the point 2,5 in the clockwise direction by 35 degree. Find the final position of the triangle. Show the total transformation on a graph paper. Field study. Visit any industry nearby where 2D drawing on a paper is used on the shop floor. Interview the engineer or technician on the feasibility of the use of a solid model on the computer instead of 2D drawing on a paper. Upload the interview on YouTube and discuss the comments of viewers in the class and WhatsApp group of your like-minded friends.